So what we expected, so if our estimates were correct, so we expected to have a center of the band gap at 240 terahertz. And we actually get this result. So this is the first band, this is the second band, and here it's a band gap. So we will see it will make final calculation for phi equal to 180. Okay, yeah, here it is. So this is our band gap. So we will work in this frequency range from 230 to 255. So let's move forward now. So we right now we have done this first task only. So let's go further. Let's solve task number 2. So we would like to calculate transmission and reflection for a finite PHC slab. So we will do this in frequency domain. So what do we need to change here? I think so. I wanted to use this another option, but I think we will skip this. So let's see what we need to change here. So first, we change type of solver. Actually, we can, well, it's not so important, but you can save this project as a new one, just so you have this result in another project. Okay, so first we change the solver. So from eigenfrequency, from eigenmode solver to frequency domain solver. Now, the frequency range from 0 to 300. Yeah, it's fine. It will cover first 2 bands. So that's what we would like to check. So materials are the same. Now, geometrical objects, before that we had just one period. Now we have n periods. So let's check. We have parameter n here, number of periods, actually not layers. So we need to make array of these layers. So to do this, we, well, you can either choose both layers or just choose first component. Right click on this component, choose transform. Okay, so what do you need to do with this? You need to translate these 2 layers. You need to copy it, and repetition factor should be n minus 1. So you add 9 more periods, and we translate it in that direction by D1 plus D2. You can click preview to see what kind of structure will be created. Transform. Well, it looks fine. Click OK. N minus 1. Okay. And click OK. So now you have these 10 periods. Okay, now before that we had 0 background in all directions. Now in XY direction it's the same because we still have homogeneous layers, infinite layers. But in Z direction we will consider incident of the wave from the vacuum. So there should be some distance. So two semi-infinite vacuum layers on the top and on the bottom. So we need to create some background distance. So it's the easiest way to implement this semi-infinite layers of vacuum, just to use background distance, because background material is by default vacuum. So we go to the background, simulation tab, background, and add lower and upper Z distance. So in our list of parameters, we have variable LZ. So we can just put there LZ in lower Z distance and in upper Z distance. So again, it's similar to what we had last time. So remember that if you have some near fields, then it might be important what is the background distance, because if you have near fields and you use, for instance, open boundary conditions or mirrors, they will be affected by these PMLs or mirrors. But if you have only propagating waves, which is the case, so here you have only plane waves propagating inside the layers, then this size is not important. So it says LZ here 100 nanometers, so it's also something around one mesh cell. So we can click OK after that. Yeah. Now we have these two additional layers of vacuum here. Okay, now boundary conditions and source of radiation. So I wanted to use another option just to show it, but to save some time, I think we will use the same as previously. It's in the last class. So we will use unit cell boundary conditions. So let's go to boundaries and change boundary conditions in X and Y directions to unit cell. In that direction, it should be open. Okay, so that's it, just unit cell in XY and open in that direction. So we don't change scan angles because we consider only normal propagation. Okay. Once we've created unit cell boundary conditions, we have Floquet ports in the folder ports. Remember that we need only the plane wave, which is the zeroth Fourier component. So this is the first mode. Actually, two first modes because there is polarization degeneracy. So we need just one of these Floquet modes. So we will change number of Floquet modes in both Zmax and Zmin ports to 1, just to avoid unnecessary simulations.
It's always to simplify the model. So continue.
It's always what?
I say we choose it to one because we want to simplify.
The first mode is a plane wave.
Yes, that's to simplify the models.
Kind of, yeah, but if we use all like 18 nodes by default, the program will simulate this structure 18 times. So we don't need that. Well, yeah, okay. So in our case, source of radiation is also the plane wave, but we use Floquet ports instead of the waveguide port. So as a result, once we have ports the CST will automatically calculate S parameters, scattering parameters, which will be transmission and reflection. There will be also field distributions once we add field monitors. So we don't change mesh. So let's first create one monitor, okay? So we go to the folder monitors, field monitors. Right click, new field monitor, field monitor at the frequency 240. This is approximately the center of the band gap. Yeah, let it be electric field. So click OK. Now let's go to setup solver and see what we need to change in the setup solver. So by default, okay, so first we want to perform some broadband simulation. So I would like to have transmission and reflection spectra in the quite wide frequency range. So for that, we should use broadband sweep. Usually it's the best option. So broadband sweep by default is general purpose, but actually it's not very good. This general purpose method sometimes. So it's better to use fast reduced order model method. Now, source type will be one of the ports. It doesn't really matter, Z-min or Z-max. So let's say we choose Z-min. Mode, again, doesn't matter because we have just one mode. Next, frequency samples. So just leave monitors. We don't need some extra simulation here, so just monitors. So once we used fast reduced order model broadband method, the scattering parameters will be calculated in the whole frequency range, and that's what we need. The monitors will be calculated like during post-processing, and if we need monitors at different frequencies, we can add them. But if we don't need this, so just leave one line monitors. And finally, remove adaptive tetrahedral mesh refinement. So we don't need this option right now. Okay, after that, I think that's it. Yeah, I think changed everything, so we can click start. So this fast reduced order model method, it's a broadband, it's an iterative method. So it calculates response in the whole frequency range, just in one simulation. So you don't need to perform simulation at different frequencies. So once the simulation is finished, you can go to 1D results as parameters. So there is Z-max1, Z-min1, which is transmission coefficient, and Z-min1, Z-min1 reflection coefficient. So this is how it looks like. What do you think? Does this look okay? So Z-max1, Z-min1 is transmission. So there are some resonances, but its transmission is close to 1 until the frequency 230 approximately, 220, 230. And this is exactly the first band. Yeah, then transmission is rather low inside the band gap. And after that, again, it's goes to almost 1. And the reflection on the opposite, so it's more like 0. So this oscillation, these Fabry-Perot oscillations is due to the finite size structure. So you have minimal reflection in the band gap, and after that it goes close to 1. So indeed, in this range of frequencies in the band gap, these 10 periods of photonic crystal, they mostly reflect light. Not ideally. Actually, maybe, yeah, if we had time, we could check like how accurate are these results. So there might be some small inaccuracy, but no, it doesn't really matter. So I think it's quite accurate. So we have almost 1 reflection in the band gap. So that's what we wanted to check. And you can see that, yeah, this result was obtained just in 1 simulation in the whole frequency range. If we had to use conventional frequency domain approach where we calculate, perform simulation at different frequency samples, yeah, then we would have to put here like, I don't know, 100 frequency samples at least, maybe several hundreds even. So it would take much more time. Okay, did you get these results? Yeah, you have, so it's the same, you have decibels. Yeah, then you have focus. Cost. No. So let's try to move further. So the last part of this frequency domain simulation, we would like to now consider the Bragg cavity, yeah? So two mirrors and this defect layer in between the mirrors. So how we do this?
First part or this the second part. Oh, okay.
It's, so we kind of still here. Yeah. Yeah. So I'm not sure yeah. Okay, whatever. Let's try to do something. Yeah. So I suggest we do it in the following way. So we take the whole component. So choose the whole component, right click, transform. And first we simply shift this whole component into plus z direction by dqw over 2. dqw, it's the size of the defect layer. Yes, half of the dqw to the plus z direction, and click OK. You can delete all the results. Yes, that's fine. So the second part, we choose this whole component, click transform, and now we choose operation mirror. Mirror plane normal will be z, so we choose z equal to 1. We also use copy because we need to copy this mirror. And click preview. So just to check that you get the same mirror on the right side. So mirror, copy, and mirror plane normal 001. Click OK. And now the structure should look like this.
Excuse me, why should click copy?
Because we want to create the second mirror. Yeah, so in...
Okay.
Yeah. Okay, actually, I realize that we've done it a little bit wrong. So the thing is that in this geometry, these two layers adjacent to the dqw, to this defect layer, are made of the electric epsilon 2. And right now we have these two layers, they are the electric 1. So how do we fix this? Can we fix this quickly? So D1, D1. Okay, let's try to fix this. Can you just, quickly, so we'll made it a little bit way, okay. So just, can you go to Home tab, click History List. And there is a list of operations which we are doing. And operation, the one before the last one is translate component one. Yeah, do you have this? So choose it and click delete. And after that, click update. Yeah, so now there shouldn't be any gap between the two layers. Okay, so now we have this defect layer. I mean, we can, so it's not very good that we've done it this way because it has fixed size. It's 2D1. But actually this, if you check this DQW is actually equal to 2D1. So now it's fine. We have this defect layer with the same thickness that we needed. Okay, so we've created this geometry. So where were we? Well, eigenmode solar. Sorry. This one, it's already time simulation. This one, yeah. So first we change the frequency range because now we need to operate only inside the band gap. So we change Fmin and Fmax to 230 and 255.